There's something going on. You explain like this, like I have to do this. I don't need like the and I just want to like only just colors through graphics. That's been
oh, yeah.
That's the great thing. I was like, Tom was there for 5 years. Because they said, I guess and I told him, I was like, yeah, math doesn't matter. Barely even read the statistics. So, like I only tapped on, I was like, yeah, it's good. So I'm going to try to you like one shirt, you get okay. Well, and also you should check
All right. How's everybody doing? Good? Yeah, good. Any questions for me to go on today? Yeah.
So there are slides for lecture 9B.
Yeah.
So if you didn't go over any of those,
I'm gonna hope to do them today.
okay.
It kind of depends on how many questions we get in this one, but it's if you looked at it, you'll see that it's contains more about optimization, like different variants of stochastic gradient and stuff. And yeah, so I'd like to go through those today. I think there's time. We'll just make sure we get through lecture 10 first, and then we'll come back to this. Any other questions?
I have a question. So I'm going to post the solution of homework 1 for the homework 2. Do you have?
Oh, the solutions to them. I didn't do that last semester. The grades. How are we doing on grading? I haven't seen the updates. Are you guys up working on them?
You're going to meet tomorrow.
You'll be submitting them? Oh, then okay, yeah. I see. Okay. Yeah, so I didn't do that before. But I could easily do that. Yeah. That's funny, nobody asked me about that last time around. I'm really not sure why. Well, yeah, I mean, so the homework, when it got graded, it was, it was putting out what was wrong, but nobody asked for the whole solution to be posted. So, yeah, let me think about that for a second. But it obviously sounds like a good idea, so probably do it. All right, let's get going. So, part 3 of our history of convolutional networks. Okay, so we did ResNet, we did VGG, we did Inception. So those were huge improvements in each year. But then we got sort of a brand new set of models that really became deep. So, you know, AlexNet, as we discussed, has 8 layers, and then, you know, we went from 8 to 20-ish. So, you know, kind of 2.5 times. That's pretty big. But then we go to the competition in 2015, and all of a sudden we're at 152 layers as the winner. And that's a huge, huge jump, right? And the question is, how did they do that? Already, as we discussed, it was already hard enough to train like the inception net, but we had to have 3 heads to keep signal coming into the network so that all the weights could be trained. So, you know, what trick happened here to allow us to go to 152 layers? And the trick was this idea of residual blocks. So, oh yeah, here's another picture of this. 8 layers, 19 layers in BGG, and then 152 layers. So, yeah, quite a difference. There you go. So, what happened here? Okay, so what we got was so the model that won this year is now known as ResNet. The res there stands for residual, and it's really just kind of a very simple, basic, but turned out to be very powerful idea. We went from nearly 7% top 5 error to now 3.5. So you basically have the top 5 error rate. So not only that, these ResNets won every single competition, ImageNet competition that year. So not just classification, but localization and the various other competitions there are. And then Microsoft had these Coco, or these competitions using Coco, which we've seen a little bit of, similar to similar to ImageNet, but also some captioning, and it won all of those as well. So like this was a huge major step forward in convolutional architectures. The basic idea is this really simple block, or this really simple kind of structure here, what's known as a residual block. So what is this? Okay, so this paper is a really nice paper to read. You should definitely take a look at it and read it. They answer this question at the beginning. What happens when we continue to stack deeper layers of plain convolutional in a plain convolutional neural network? So just like BGG, what happens if we just keep doing that over and over and over again? So it turns out that the error, so 20-ish layers, that's like BGG type or inception type of network. But if you just keep stacking those layers, it turns out that your training error actually increases. So the network's actually starting to get worse. So you're increasing depth, and like the story we've been telling is like, it's the depth that's really allowing you to learn all these additional like abstracted features and really be able to do much better. But it turns out that if you just keep doing that, unfortunately, you quickly find that your training error, your test error, as a result, these are getting worse. You're not improving the ability of your network to learn. You're actually making it far worse. And this has like a lot of reasons. It's definitely not overfitting, right? It's not that like if the training error went down, the test error went up, that would be like an overfitting scenario. This is just a general behavior that happens because we just start to like lose the ability to learn in these networks, to pass meaningful gradients all the way from the head of the network all the way back through the rest of the network. So yeah, this is a way to think of this. This is an optimization problem. The deeper models are harder to optimize, right? That's what I said earlier about the gradients. They're getting smaller and smaller, not providing enough signal to update the weights is the problem. especially as you are increasing the size. You know, as you increase the depth, you're basically increasing the size of the parameter space you're in. So this is an optimization problem. So how can we fix this? So, you know, deeper models should be able to perform at least as well as shallower models. That's like a hypothesis we ought to go on here, right? So like, if this just sort of makes sense, right? If I can learn something in 20 layers, and then I just add, like to that architecture, I just add another 20 layers or even one more layer, like I should be able to learn exactly the same thing and maybe a little bit more with that extra layer. You know, especially if that extra layer like has the ability, for instance, to be the identity layer, right? Like theoretically, my network, my deeper network has the capacity to learn as much as the shallower network did. All other parameters being held constant. So we want to. So this was like the key idea that this team at Microsoft followed in thinking about like how to overcome this problem of having worse performance as you get deeper, very deep networks. And it's this idea of like being able to have an identity mapping involved. So solution, use network layers to fit a residual mapping instead of directly trying to fit a desired underlying mapping. So here's the idea. So, you know, here's just like your BGG type of construction. Convolutional network, or convolutional layer, activation, convolutional layer, activation, so on and so forth. Maybe some pooling, what residual networks do, what ResNets do, is they have this concept of residual block. And you preserve this, like in the basic setup, you preserve this structure of just having a convolutional network and activation convolutional network. But you do one very important thing, and that is you take the input to this whole block, and you have what's known as a skip connection, and you basically add it back into whatever transformation has happened through these convolutional layers. So that the output from this is not just the transformations F of convolution rate of convolution, but you've added back in the original. So this is why these are known as residuals, is that because you're giving the network at this point the input to it, all it has to learn is the residue or the residual here kind of left over from this map. And again, like this is trying to take advantage of like this theoretical idea of like, hey, I should be able to learn exactly, the deeper network, I should be able to learn exactly the same thing as the shallower network. And why don't we just kind of push it in that direction by trying to just not making it learn all the transformation, but just making it learn the difference from the input, right? So you can think of this as learning the difference from the input. It turns out this is like way easier for the network to do, and it worked really, really well. Yeah. Use these layers to fit residual, learn the residual F instead of just the full transformation directly. Yeah, so that's it. That's really all it is. There's a couple things that should be noted here. If we're going to add these things together, what has to be true about the dimensions of F? Yeah, they have to be the same as X, right? So like this is actually constraining us a bit here. We can't just we have to, for instance, preserve the number of channels in the spatial resolution in each one of these blocks. And that's what like the plain vanilla ResNet looks like. Is it starts off, so you have your input, and then it starts off with a 7x7 convolution. So it's a little bit like original AlexNet that had this like large 11x11 initial convolution. Has a pooling layer, but then it then just builds this network as deep as it would like with these residual blocks. And what happens, so you see these are different colors. So, one question you might be asking yourself is, well, does that just mean like that the feature maps stay at some very large, spatial extent? And the answer is they remain the same. So like this pooling layer is going to reduce them a bit. So let me point out a couple of things. So this 7x7 convolution has this kind of /2 in the architecture. So there's 64 filters. The /2 is a stride 2. So that already, downsampled by a factor of 2. This pooling did the same thing. So it's already downsampled by a factor of 4. And then every time you go into one of these new colors of residual blocks, you get another stride 2 convolution. So these are known as like the stages of the ResNet, each of these different colors. What happens is you get a doubling of the number of filters. So like notice here you go from 64 filters to 128. But as you enter it, you get a stride 2 convolution, so downsampling by a factor of 4 across the whole spatial extent. But so there's kind of like this preservation of like number of filters and the stride that we take here. And you basically build up ResNets out of these stages, these groupings of these. So again, within each of these colors, within each of these stages, the spatial extent is preserved, and that's how we're able to do these skip connections of the input. So like, whatever the input is here, it travels this path right here. This is like that F, and then you add to it X, and then we do that again, and we do that again, and then we get a downsample in here. So this skip connection also has to downsample, and so forth. So and the way that downsample is done is just through a basic linear transformation. But yeah, that's how it's done.
So, does the parameters of layers within the same color block share the same parameters?
They don't share the same parameters. No, these are each their own convolutional layer, just like any convolutional layer. Yeah, so like there's 60, like in those kind of red ones, there's 64 filters, right? Mm-hmm. So each of those layers has 64 individual learned 3x3 convolutions all the way through. It's just, again, it's the coloring there is to express the fact that they all kind of share the same spatial extent. So, if these were if these were like the ImageNet 224 by 224 coming in here, and we get a stride 2 here, so that takes us to 112 by 112. This takes us to 56 by 56. Then that remains 56 by 56. Then we get to here, and this stride 2 is going to take us to what is that? 28 by 28, and so forth. But they're just convolutional layers. But again, you just have these skip connections where you're just adding back in the input at the end, so that it only has to learn the difference in each of those blocks, the difference from the input. There's a couple other questions, well, a lot of questions, yeah.
Two questions about the skip connection.
Yeah.
How exactly does it work? It adds to the
Yep.
depth, or
Not to the depth, it literally adds. These are two tensors of the same size, and they just add entry-wise.
Not concatenate?
Not concatenation. Nope. This is like truly adding, so that you really are element-wise. So you really are learning the difference between
how
the.
makes the optimization easier.
Yeah, we'll talk a little bit more about that in a second. But I'll just say it one more time that because you're giving it like its input, it only has to learn. It only has to learn so whatever the output should be, it only has to learn whatever the difference that should be from the input, rather than like the full output all by itself. So it's a little bit like a boosting algorithm where in boosting, you just kind of fit the residuals as you go along in the ensemble. And that's exactly what's happening here. Is you're just having to fit the residuals from the difference from where you're at right now in the next block. So it just becomes an easier problem for that reason altogether. So let's see what's going here.
If you want to learn the difference between the function and the input itself, we should subtract or divide or something like that.
Yeah, like if you want to know exactly, if you want to know what the f was, you'd have to subtract off. Like from right here, you know, there's two things. Listen, each one of these is just an adding operation, right? So you have the output from here F, and then the output from here X, and just adding them together.
How is it learning the difference between these two by adding those?
Well, it's not. I mean, it's learning it because you're giving it X. So it doesn't like you're giving it X. It doesn't have to learn that. So the full signal is H, but all it has to learn is the different, like, right? It's the learn parameters are in F, not the full H. Yeah. Yeah.
Since it's element-wise ID,
Yeah.
and but here you doing some review block, you just resize it, reduce. The
No,
size
Rayleigh doesn't change the dimensions.
Because
You're saying when we enter a new stage, you're saying these drive twos?
yeah.
Yeah. So there's actually there's
a
a learned linear transformation. So there's like a matrix multiplication of the input to go down to the right size. There. So there's actually a learn, like that skip connection is not an identity. It's a projection. Yeah. So there's additional learn parameters there as you change stages, because there's got to be some way in these to reduce the spatial extent, because that's to be able to increase the number of filters, you really have to reduce the spatial extent. Otherwise these blow up. Although what we're going to talk about later on in this lecture is wide residual networks, which actually actually increase the number of channels, but don't get as deep, and they perform just as well. Were there other questions? Yeah.
So like adding more layers would basically never do worse than
That was the idea that they were trying to build on here was it should never be the case that when we add layers it should get worse, because all you're doing is increasing the capacity. So they just thought, hey, let's just make this easier for it to learn the identity function as you go forward here, right? The identity function here is for F in any one of these blocks to be 0, right? Because you're already adding. I mean, the skip connection is the identity function, right? You're just taking the input and bringing it to the output. So to learn the identity function, F just has to be 0. And that's very simple to learn compared to like the straight up identity from a bunch of stacked convolutional layers. Yep.
Does this also help with the network connection of the gradients, or is it
Yep, absolutely. Because again, there's no signal from the gradient coming through the identity maps. There aren't any parameters there except for in these connections where it has to reduce the spatial extent. But these, like, because you're learning the difference, like you sort of, this is not quite right, but you're sort of adding like a directionality to the way it's learning. So like at each stage you're learning you're learning the residual. So you're learning what's left over from the one before. So it's like the maximal signal to learn, rather than kind of like something being washed out by that idea continually moving. Okay, one more question.
Yeah, so here the X has been transformed twice before it's been added, right? So we have two convolution layers, but the equation only there is a one fx. So that's
this fx is maybe I put a curly brace here. It's this whole thing. Let a convolution rated convolution.
Okay, so there are two.
That's F. That's F.
Okay.
Yeah. Okay, so that's the plain vanilla ResNet. And then if you look at the very end of this, at the head of this, there's a pooling layer that's actually a global average pooling. So like the inception net, that it just takes the final feature map, and then for each channel, it just takes the average of all the values at that channel, all the spatial values of that channel, just averages it. So that this goes your output will be of whatever the spatial extent is, but of 515 channels. So that when you do global averaging, that becomes a vector of 512 size 512, so 512 numbers. That's what that pooling does, and then that just does directly a connection to a fully connected layer of size 1,000 so that you can apply softmax so that you can do your classification. So again, these things all avoid the massive numbers of parameters that you get when you have a couple of fully connected layers there at the end to transform you from your feature maps to your output size. Okay. Yeah. Should have been giving these, but right, we already talked about that. We already talked about that. Yep, and again, we already talked about that. So, great. Okay, so the paper has a couple of different suggested architectures, and there are size 34, 50, 101, 152. So these are now known as ResNet 34, ResNet 50, ResNet 101, ResNet 152. So you're never talking about just a plain like a ResNet without a number on it. So ResNet just kind of suggests what the architecture is like, but then there are these accepted architectures that were first laid out in this paper. So the ResNet 34 is the architecture we've been talking about. When we go deeper, like 50, 101, 152, the architecture changes a little bit, actually quite a bit, it turns out. So, so this is very much like what we learned about in the inception net. So you start these as the number of filters increases, these 3x3 convolutions become more and more expensive. So this idea of using the bottleneck is preserved. So here we are at some point in our network where the inputs of size 28 by 28 by 256. So the idea here is in each one of these blocks, instead of it just being 2 3x3s and with a radio in between, you first use a 1x1 to, usually what the rule is to compress this to a quarter of the number of filters. So that's, you can do 6 divided by 4, you get 64. So 1x1 suggests change the depth, the number of channels, and then do the 3x3 convolution. So that's just far less expensive. And then to use 1x1 convolutions to expand out again to 256 channels, so that you're back to the same size, so the same number of channels, so you can add the input to it. So this is this idea of bottlenecking. It's you compress the input, then do the operation, then expand it again. So there's now 3 layers instead of 2 layers, but there's far less parameters. And these bottleneck residual blocks are used for ResNet 50, 101, 152. Is there anybody out there who's like, I don't understand why we do that? Like, why don't we just?
Yeah. Why the additive function?
Oh, you're going back to the original, yeah. So the very simple. So I've given you a couple of answers that are kind of theoretically why it is, but the very simple answer is that using architectures like this have the number or have the top 5 error rate. So it's clearly way better, right? But again, you are preserving. You are making it easier for the network to obey the property that you want, which is deeper networks should not be worse than shallower networks. Because again, let's if I take a network of n layers and I add one more layer to it, and that layer is just the identity layer. I fix it to be the identity layer. It doesn't change the output at all from the previous one. By construction, there is a network that is deeper, but that should preserve it, right? So you're making it easy for the network to behave that way by always giving it the input from the previous layer exactly, so that it's easier to learn the identity if it can't if it can't learn anything else. And it really is the case that these deep networks, many of like the final layers will be very close to like identity. Like those functions f will be like nearly 0 if it doesn't if it can't learn anymore. So it won't get worse. It'll just preserve the capacity.
Why is it easier to learn 0 than like identity than something else?
Because 0, especially with regular activation, 0 is just really easy to get to.
You just have a lot of area that's 0.
There's a lot of ways to get to be 0 in a ReLU network. Yeah. And then obviously you have biases too as well. So like, but that's still is very easy to be 0. Yeah. There's lots and lots of regions for space for it to be 0. Okay. Yeah, I keep telling you these things and I don't think they're. Okay, so a little bit more about ResNet, what was done here. So this wasn't pointed out in the architectures, but batch normalization followed every single conv layer you saw in the previous pictures. So this is coming after Inception version 2, where batch normalization was introduced. So they're using batch normalization 2. That really, really helps in terms of just being able to train this thing, especially with these deeper layers. So the identity part is helping, but some of these other things are helping as well. They used a different kind of initialization that was more appropriate for ReLUs. And we're going to talk about that a bit right now. So remember that we learned this last time about how to initialize like the Inception network. This particular rule of drawing from randoms, but that are centered at 0, but whose standard deviation is determined at each layer by the number of inputs. So that was done under the assumption of linear activations. So this group redid that analysis with ReLUs. Yeah, so if you use ReLUs, this idea idea starts to break down. So the deeper you get, the more likely it is that randomly initialized layers will have outputs that look more like 0. And this maybe wasn't such a big deal for the networks of the depth that were being used in like Inception or VGG, but when you get very, very deep, this became a really big deal. So they redid the analysis, thinking about ReLUs, and it turns out that the new rule should be that. So instead of dividing by the square root of the number of inputs, you divide by the square root of 2 over the number of inputs. And you get this nice kind of preservation of the distribution. This is now known as key initialization, and like most frameworks will have this as an available initialization for your parameters as the key initialization. Why does it work? You need to read the paper to sort of believe it. It's really, if you think about it, it's very different. Very, very different than the other one. The scaling parameter is actually quite different. And I don't actually have a good intuitive explanation for you of why that is. Unlike the one I had before, like calling the central limit there. This is more just like, hey, if you you do some math with ReLUs, this comes out, and voila, it works. So anyways, key initialization is important here. And because so many networks now are, convolutional networks they look like ResNets, this is used very, very often. Yeah, I think a good convergence. Okay. Yeah, so like I already mentioned, these were trained to 152 layers. I'm not really sure why like 152 layers, why it stopped there. They do have some results where they trained like on 1,000 layers, and they got essentially the same results as 152. So I don't know if they like at some point just was like, 152 must be good enough because it's the same as 1,000. But that just sort of became the depth that's you'll see this now a lot. Like 152 is a depth that people use all the time, mostly in ResNets. And yep, these, like I said before, this won everything that year. So a really great year. It really showed like a huge step forward in designing convolutional networks. Yeah, so you see like the ImageNet classification, detection, localization, and then Coco had its detection and then a segmentation task as well. So winning by huge margins. It's pretty cool. Yeah, question.
So can you kind of tell us exactly what those last three are testing exactly? Is localization just saying like draw a square where this image is, and what's Coco detection and Coco segmentation?
Yeah, so classification is the task we've been talking about. There's one object in there. Detection is detection of one or more objects in the image, and localization is like drawing bounding boxes around those. And that's the same thing for Coco.
It's just a different data set.
That's for detection. Segmentation is like a semantic segmentation, which we'll talk a little bit about here in a couple of weeks, where it's like there's a person in this, and here are all the pixels that correspond to that person. And here's a tree, and here are all the pixels that correspond to that tree. Yep. Other questions about that? One more thing that we didn't point out, but that should be pointed out, is that this was the first year when a network did better than the human does at this task. You remember the human was at a 5.1 on average at the top 5 error rate on this task, and now these are doing roughly 3.5, 3.6. So we now have networks that are outperforming humans in a particular task. So not only did we win all these things and super impressive like reduction in the top 5 error rate, it's now below the human error rate. So AI is out to get us now as a result. Okay. So what could there possibly be more of now? So we now have like a lot of different networks we could be thinking about. We have different BGGs, different ResNets, different inceptions. There's a couple other networks on here that we'll talk about. We haven't quite talked about yet. What's interesting now is you can start to think about them in terms of like various dimensions. So like how many parameters they have, how many operations they require, and like what kinds of results they end up getting. So this plot's trying to these two plots trying to get all that information all at once. So here's your top 1 axis. So we've been thinking about this in terms of like top 5 error rate. Here's your top 1 accuracy. So like all these networks that we've seen so far, they're basically like the ability to pick out the right answer, the rate at which it does that across all of ImageNet. So you see our ResNets here. On Inception version 3 was this. So we mentioned it last time where it has batch norm and then these like factor convolutions in the Inception modules. And then this Inception version 4 is basically a combination of Inception and ResNet, using residual blocks in the modules. Okay. By the way, I didn't say this, but the size of the circle for the network is the number of parameters it has. So a couple things to note here. Inception version 4 is that plus that. BGGs, so they have the highest memory costs, most operations. So they're the biggest circles, and they're the furthest to the right on that axis. And they're only getting, they're not getting very, very high accuracy. So BGD's, kind of one, but again, you don't really see people using them much, except when someone might use a pre-trained model. This just sort of for historic reasons you see a lot of. So notice AlexNet over there, or sorry, Inception. Very, very, very efficient. So it's getting about the same top one accuracy as the BGGs, but far smaller parameter print in terms of size or memory, and also number of operations required. Remember, this was like BGGs had like in the hundreds of millions of parameters, where Inception had about 5 million parameters. So quite a big difference there. AlexNet now is like the worst of all these. And ResNets are way up there. They're kind of a nice balance of size and operations for a whole lot of accuracy. And one of the reasons why you still see a lot of people using ResNets and variations on ResNets today. You can kind of tune that balance really, really well. Yeah, there's some more numbers here we can talk about in terms of how much time in the forward pass, how much power they take up. Let's go on to other architectures. So, so we're going to go through now just a bunch of other architectures, including the ones that won the subsequent years of the ImageNet classification task. So this one didn't win any classification task, but it's worth pointing out this network and network idea. So this sort of was the inspiration for the InceptionNet and GoogleNet. And the idea was, you have these convolutional layers, and all that. So the convolution will take any region, like a matching region size in your image, and turn that into a point. So what network and network did was to simply put in a shallow set of fully connected layers in between the convolutional network and the output to that single value. So there's like this shallow network being learned within each filter. And I mean, I don't think I've ever seen this really used seriously anywhere, but this idea that you can kind of combine these things together did give rise to this, so it's sort of worth pointing out just from a historical perspective. And you might see reference to it every once in a while. What happened after ResNet? So the Microsoft team that created the ResNets and submitted and won everything, they started really like iterating on their ideas. So one thing that they did was to change what the residual blocks looked like. So if you remember, the plain vanilla was like a convolution, and then a ReLU and a convolution, and the batch norms followed each convolution. So these batch norms were in there before, but what they simply did was instead of applying the ReLU, so these things would, I didn't point this out, I guess, but these things would be added together, and then a ReLU would be applied to that. But instead of doing that, they brought this like a batch norm and a ReLU inside of the residual block to be like the first thing that happens, and then have this convolution, batch norm ReLU convolution. So like basically this is what we had before in the plain vanilla blocks, and now you have this. And it turns out, and what you don't have is you don't have the batch norm ReLU being applied up the top. And it turns out actually this is better. You get actually better performance. It trains faster, and you get lower top 5 error. So this is known as ResNet version 2. There's a 1.5 as well. Hold on a second. Which one's it? If you use Keras, you get, and you just use what's in their model zoo, you get 1.5. I'm trying to remember what 1.5 is. I'm pretty sure this is version 2. But anyways, these are the blocks you should be using. So you should check your networks and make sure these are being used. If not, you should just write it yourself. It's not that hard. Okay, some additional ideas here. So this paper came out the year after wide residual networks, and the point that they argue, the authors argue in this paper is, yeah, the depth, the residuals allowed you to get to very deep networks, but really it wasn't the depth that mattered to you. It was just these residual blocks. It was just this ability to just focus on learning the difference from the input. And so they went about proving this by making these things wider, which wide is a weird word here. It really is that so these were established these were designed in the following way. So you take your blocks the way take like a ResNet 50 or something like that, and then just take the number of blocks there. So they had a new parameter k that just multiplied. So k is some integer, some non-negative integer. So it's so if you have so you had 16 before, and this k was 2, you now have 32. Or if this k was 10, you now have 320 or something like that. So they really just increased the number of channels. Just really made them these filter maps. Really wide is terrible because you have already like width and the height of the spatial maps, and really it's the depth of the number of channels in the feature maps that we're talking about here. But the width here is we just have way more channels now. Yeah.
So you're not changing the dimension in any sense?
Nope.
You're not adding like a fourth dimension besides k?
Nope, not adding a fourth dimension. Nope, exactly. This is just having way more channels by like a certain fixed whole integer factor. And what they showed is that you can with just a 50-layer wide ResNet, you can do better than the original 152-layer original ResNet, just by having more channels. So the argument is increasing the number of channels instead of the depth is just as good, maybe better, and it's computationally more efficient because if you think about filters, additional filters is like an embarrassingly parallel operation. You can just have the filters on different GPUs and calculate the same thing, or concatenate them all together.
So what's k? Is k just decided randomly as a hyperparameter?
Yeah, it's a hyperparameter. And in the paper, they just choose various k's and show that in this range of k's,
Gotcha.
It was better.
Right.
We got better results. Comparing the 50-layer wide ResNet to the 152. So architecturally, everything's exactly the same. You're just doubling or tripling or quadrupling or whatever the number of filters in each stage. That's it.
Plot that.
Yeah.
Yeah.
Yeah. So it's a kind of hyperparameter search. Yeah. So again, you don't see these a ton. It's not like you go out in Kaggle right now and look at the winners and they'd be using these, but they have their place in the history because they do perform better than the 152 layer ResNet. You do see these. These are interesting. So these are called ResNets. So they do the following. So again, this is from the Microsoft group. So instead of having just this one path, this one bottleneck path, what they did was to have many different paths here that all get added back together. So notice that the big difference here is instead of there being just like one bottleneck convolution from 256 to size 64, and then your convolutional layer 3 by 3, preserving that the number of channels and then expanding back out again. Do that multiple times, but you really compress each of these initial the input with these initial 1 by 1 convolutions down to, in this case 256 to 4, and then 3 by 3s, and then expand all the way back out to 256 and add that all together. So it looks a little bit like the Inception module, but this is just a repeated pattern, right? This is just it's the same exact pattern, but you just have far fewer filters that you compress down to, but you have more of them. So this is just like a different way of kind of playing with the capacity and where it all goes. And this is just sort of spreading it out amongst sort of independent. They're not really independent, but these independent pathways from the input, but then bringing them all back together, and then finally adding the input to the addition of them all. Go ahead.
I don't quite understand why you would do this rather than just have more filters. I guess it's a few less connections because you have paths and
yeah. So one of the important aspects of this is that like these are like 3 by 3 convolutions and 4 filters are very inexpensive. You're doing that 32 times, so there's like a balance here. So these can become, like more efficient that way, depending on how you choose the number of channels you're doing and how many paths are in each module. But it's also that remember this is all being supervised all at once. So like this is learning 4 3 by 3s, and that's doing it 32 times. So that's, what is that, a total of 128, where this only learned 64 3 by 3s in like the same module. So it's actually learned a whole bunch of other like features. It's a way of learning a bunch of additional features just at a different like channel depth. So I mean, honestly, a reaction I think that you're having maybe a little more deeply is like why should this be better than that? And there's really no good why, like theoretical why. Like it's always like, hey, this worked, this was better, and then our brains turn around and try to tell the story of why, without there being like a formal proof of why, right? That's really what this is. This is like confirmation bias. Things that work, we find explanations for. But that's but it's also not untrue what I said about that. You are having an opportunity to learn a whole bunch of other like additional features where each filter is a feature. But notice that again, like the residual piece is preserved. This is like a common theme. So ResNets, not to be confused with ResNets, which sound very similar to each other, obviously. Okay, other things came out of this. Another group did this, where it's a little bit like Dropout, but because these are really pretty simple building blocks, where within a stage the size of the output's the same as the size of the input, you can do like a lot of this kind of building block type things, and so there was this idea to like at each training pass just drop out entire blocks from within the network, right? So like what they're showing here is, here's your full architecture, and then you just sort of, like with Dropout, you have some probability of dropping a whole block, and then you just sort of drop those out, and then you learn through the remaining network, and then you get this like, really robust network at test time, and you use the full network. So it's again like it's building this kind of like ensembling idea like Dropout does. Yeah, I mean, again, like I don't see this being used a ton, but it's some other idea that kind of built off of this residual network idea. Yeah, this network. So let's go on to the next year. So notice that there's no name here for 2016, because for 2016, the winner just kind of cleverly ensembled a bunch of existing networks. So it ensembled an Inception v3, an Inception v4, an Inception ResNet v2, which I don't even know what that is, to be honest, a ResNet of depth 200, and then the fusion of the ensemble of these things together with, I don't even know what that is either, actually. What is that? That is, oh, that's a wide residual network, yeah. So with a wide residual network. So ensembled all these things together, able to get down to about 3% top 5 error rate in 2016. So no like innovation in the no innovation in the architectures, just a clever ensemble. So kind of like a sad year, I guess, for this. But then in 2017, you got yet another iteration on the residual network idea, and that's this squeeze and excitation networks. So these are again, these are there's really no like the reason why somebody might try this like sort of is clear, but like why it worked and why it's so much better, it's not like clear to say why. But here's how this works. So you can do this with any network, but they applied it to ResNets. In fact, they applied this to a ResNet of size of depth 152 to win in 2017. So the idea is the following. So at every stage or every layer, or after every block, you have some sort of output, which is this tensor of feature maps, right? So you might want to like sort of scale those before you send those as input to the next block. And that's what these do. So what these do is, so you have your output there. So you see a C by H by W. So that's C's number of channels, and then height and width. So we're somewhere in the network, this is the height and width of 28 by 28. And then we have so many channels. So what this does is this does a global average pooling. So that takes us from C by H by W to C by 1 by 1. So this is just reducing us down to a vector of size number of channels. And then we do a fully connected layer, which reduces the number of channels. So it's C divided by 16ths. And then we do another fully connected layer that brings it back out. So this is like a little bit bottlenecking operation. And then you apply a sigmoid, which I said never do this, but here it is, and it wins. You apply the sigmoid to like the linear output here, and then whatever number comes out there between 0 and 1, you multiply that with its corresponding feature map. So like this gives you C values between 0 and 1. Multiply each of those values, so like the first value with the first across the entire feature map, the second value across the slice, this is the second across the second slice, and so forth. And then you just add that to your input. So it's like a learned scaling of the entire slice in the feature map for each for each channel. It's just a way to learn it. You can apply that anywhere, right? So like you can do the same thing in the Inception module. This is just taking your feature map and learning to kind of rescale it, given like the content in it. And turns out when you do this, you get even better networks.
So here the residue itself is a residue network, yes, or residue itself.
Yeah. So this is in a ResNet. So this is just being added to the. So like in this case in the ResNet, you'd have your output from your block, your residual block. That's what that is up there. That rectangle is a residual. You do this learn rescaling, so now you rescale the output, the feature maps, and you add the identity to get the final output.
What is the scale? Does it just multiply the output of sigmoid with output
Yeah.
of the residue?
Channel by channel. Exactly. Yep. So you're just taking the residual, like the first channel gets multiplied by the first number here, the second channel gets multiplied by the second number, and so forth. So it's learned to scale, and we're going to see things like this as we look at like recurrent neural networks that use ideas of attention. This is a lot like an attention mechanism. This is a lot like having a gate to say like, hey, pay attention to these channels and not to other ones. That's the scaling between 0 and 1. Anyways, when you do that, turns out you get even better performance. So they applied this to a ResNet. ResNet 152, and they want to see. So note that they go from 3.6 to 2.3 by using the ResNet and doing this squeezing excitation. So it's kind of a weird name, squeezing excitation, but the squeeze part is just, squeezing this feature map down to these numbers, and the excitation is like as a call out to using the sigmoid to get a scaling between 0 and 1. Okay, so that was 2017, and then after that they discontinued the competition. They're like, okay, we're done doing this. We need some other competitions to take over here and push this forward. Okay, so what other ideas are out there? I want to get to the optimization, so I'm probably just going to go quickly, really quickly, like 30 seconds through these because they're not super important. But there's this idea of so these are other ways of getting at depth that aren't residuals. So there's this idea of fractal net, which is like just building up these. It's taking a bunch of convolutions and like putting them together, concatenating them together in certain ways to give you some sort of final output. So there's kind of an idea, like not a residual idea, but this idea of like breaking up the computation into smaller pieces and then bringing them back together again through different subpaths. And it's a thing. You actually see these a lot, dense nets. These are pretty cool. So they look a lot like VGGs in terms of like convolutions and pools. But then every once in a while you have what's known as a dense block. So a dense block is again like convolutional layers, but the idea is you see these concatenation layers. The idea here is to like continually bring back the previous layers into downstream layers. So you learn this convolution, and then you concatenate the output of that with the input that went into that convolution layer into here, and then you do another convolution, and then you concatenate with that both the input and the output from the previous convolution layer, and you concatenate all that together. Do it one by one, concatenate everything that's come before, and do another one by one, and then that comes back out to this convolution. So this is a little bit like residual networks in the sense of this input's continually being brought back, like up to ahead into downstream layers. But instead of it being in this addition way, that's this truly residual way, it's just concatenated with additional features. So you just have like more features. This is used all the time, and like cabinet competitions are one, incidents and things like that. So these are cool networks. Yeah, we won't go through this. I'll say this briefly. So there's a whole area of neural networks known as meta learning, which is like learning the architecture itself. So when we talk about hyperparameter searches, we usually think about like a family of architectures, and we just kind of play with the parameters. So like we'll start with ResNets, and we might change the number of filters, number of stages, number of blocks within each stage, so forth. This is like a way of like totally being able to build this up out of like arbitrary blocks. And the weird way that these work, like the paper being cited here works, is that you basically have a string that represents your network and all the parameters in it, and you have this controller network that that with a certain probability will like manipulate that string to give you a different architecture, and then gets rewarded like in a reinforcement learning kind of way, which we haven't talked about yet, but gets rewarded in a reinforcement learning kind of way if the resulting network that comes out of that is actually does better in accuracy than the previous network. So what it manipulated from. So like there's like some string representation of your network. You make a change. If it's better, that network that's learning to make those changes to the string, to the architecture, gets rewarded, and it learns to take, you know, wherever you like whatever architecture you're starting from, and to like make updates to it so that it's like better than it was before. This is a huge area. We're not going to spend any time really learning about meta learning, but just calling it out that this is something that exists, and you know, people use it at times. Okay, let's jump over the 15 minutes we have left and do a little bit more optimization. Any questions on all that before I do that? Yeah.
So, a couple questions. First of all, which of these are still being used today? Right, just kind of like an overview.
Yeah, so I did try to point that out while I was going along. I mean, so like ResNet, you see ResNets all the time. ResNets, like you just even like ResNet 50, ResNet 101, with ResNet 152s. Most deep learning frameworks will have those architectures, like they'll exist in what's known as their model zoo, with pre-trained weights usually on something like ImageNet. So you could train it yourself. They have the whole architecture there for you, train it de novo, or you could train it, or you could use it with pre-trained, or you know, with these weights, like the winning weights from the competition, or you could do some transfer learning where you start with those weights and then like learn a different data set. So ResNets, you see a lot of. Dense nets, you see a lot of. There are other nets like efficient nets that you see a lot of that we didn't look at today in the convolutional network area. Did I say dense nets? Yeah, dense nets are definitely used. So usually, like most people will start a problem using some variant of a ResNet if you're doing convolutional networks. Yeah.
So when you're doing transfer learning on these, I know that Keras has the ability to like give you everything but the fully connected layer, so like you can do it for you, fine tune it for your.
Yeah, and all deep learning frameworks have a way to do that.
So is there a way to learn still in the convolutional layers without treating it like a new model? If that makes sense. Is there like
yeah, I mean, so the way this works in any of the frameworks is you have what are known as like frozen or frozen or unfrozen parameters or layers, and you can at any time with whatever you're doing, you can choose to freeze or unfreeze certain layers. So what that means is a backward pass will not update the parameters of a frozen layer, but it will calculate the gradient through that layer given those fixed weights. So you could freeze and unfreeze different layers and then learn those. It's not typically what's done. It typically is something that's pre-trained like on ImageNet. The reason why you only like retrain the final fully connected layer or like final convolution layer or something like that is that the assumption is that you've learned just very general filters that are good for like any image problem, early in the network. And it's only at the end of the network that you want to like kind of learn to like reweight those appropriately for your new data set.
And that's fair well in history.
Yeah. Oh yeah. Like transfer learning is one of the best. Like you should pretty much always start any problem you're doing. Like it's like if you're doing a problem that requires you to do something with ImageNet-like images, you better start with something that's pre-trained on that, like one of these networks that's won in the last couple of years. You'll just save yourself time, money, heartbreak, all kinds of things. Because again, like you're starting off with filters that are like really good already. for processing natural scenes like what's in the internet. All right. Yeah, one more question.
I did understand why ResNet module works, but I didn't get quite dense. What's the intuition? You understand?
So nothing more than what I said is that you have these connections where you're bringing the input up so downstream, so up in the network. So the downstream layers don't just get the transformed input; they get the actual input itself. But instead of adding these things together, you're concatenating it. So your input to the next layer is like the original input plus the transform features from the layers before. So it's not residuals, but it's like it because it's being able to use the original input to learn in deeper layers. That's it. All right, let's do this. More optimization. All right. So a couple other ideas that we talked about stochastic gradient descent. We talked about with momentum and Nestor of momentum. So let's look at some of these adaptive learning rate methods. So a major one here is Adagrad. So what it does, this might look strange, but the idea is the following. So you compute the gradient like normal, and then you sort of keep track of the square of the gradient. So notice that this is a Python plus equals, which means that the gradient starts at 0. The gradient squared, this object is starting at 0. And when I make my first pass through here, like the first thing this looks like is just the square of the gradient. But as I do each iteration, I just keep adding the squared gradient to all the previous squared gradients. What do I do with that? I do what I normally do. I have my learning rate. Notice there's a minus equals here, so I subtract from my weights wherever I'm at right now my gradient times this learning rate. But then I divide by the square root of the gradient squared, which again, like in the first iteration, is just the actual gradient squared, but like 10 iterations from now, it's 10. It's the previous 10 gradients squared all added together. And all these operations are happening element-wise. This is just NumPy here, so this is just all happening element-wise. So what that means is that this learning rate is being adapted or changed by whatever the size of the square root of the grad squared element is there. And there's just that adding of the 1e minus 7, 10 minus 7 is just make sure that if we have any zeros, we don't divide by 0. So don't pay attention to that. But this is known as like an adaptive learning rate. So like, what's going on here? Yeah, what's happening here? So if I'm moving in a direction where it's very steep in the loss in the loss surface, or that means that the gradient is really large. If I divide by that, so I'm taking the square of it and taking the square root, so I'm getting some positive number there. If I divide by that in that direction, then that's a very large number. So dividing by that's making this smaller. So in the very steep directions, I'm actually like dampening the gradient, so I'm not moving as much in that direction. And in the flat directions, where this is small, I'm now dividing by a small number. I'm actually making that part, so that the learning rate there much larger. So I'm actually like promoting, accelerating in those directions that are flatter. And you're doing it in this weird way where you're like keeping track of all of the squared gradients that went before. So you just keep adding that. That should feel very weird. And one of the reasons it should feel weird is this question right here. What happens to the step size over a long time? Yeah, like this. We just keep adding positive values here, right? Well, at least non-negative values. It could be 0, I suppose. But we just keep adding like non-negative values. So if they're positive, we just keep making these larger and larger. So like these, if you think of this as adapting the learning rate, then it's getting smaller and smaller over time. And that's right. So that may not be the best thing. So there's another very related algorithm here called RMS-prop. That's like famously in it's in no paper. It's actually in a lecture by Jeff Hinton. Like RMS-prop is when you cite it, you cite a lecture done by Jeff Hinton. But this looks almost exactly like this, except that you're now decaying this gradient squared every time. So this looks a lot more like these momentum terms, these exponential decaying momentum terms that we have over the momentum. And our RMS-prop is fairly popular to use. If you remember this picture here, so we talked about stochastic gradient descent, momentum, Nesterov. What's the G there? Anyways, the Nesterov momentum, and then now you can see what Adagrad does, and then what RMS-prop does. So they both are, Adagrad and RMS-prop are tracing out much more direct trajectories to the minimum here, and the reason for that, of course, is that the way that you adapt the learning rate in the different directions, there's a signal to go in this direction quite steeply, but because we dampen it, it doesn't do that, and it sort of balances that out with the other directions there are. In this case, it tends to go to the right direction. And like in this particular case, it's sort of RMS-prop and Adagrad sort of converge together at the same time. But I don't know. This is just for one example. Yeah.
So I get that Adagrad slows down, Adagrad slows down, like visibly compared to the others. But why does RMS-prop also do the same thing? You're not like significantly increasing the magnitude. If that makes sense.
Right. That's just because as you get closer and closer to the minimum, like the gradient's becoming shallower and shallower, right? Like they all get slower as they get closer to the right. So like there's two factors contributing to why this might slow down. And the one in Adagrad is that you will actually literally slide by larger and larger numbers. But as you get closer and closer to the minimum, it's just going to slow down anyways. Yeah.
You said that Adagrad accelerates the steps as we draw flat regions, but I'm not seeing how that happens.
Well, it's your gradient's small there, right? So you're dividing by the square root of the square of that. So it's like an absolute value of that.
But I thought it's accumulating the past gradient, so like the denominators just progressively get bigger, and then
that's true. It is, but like if it's always small compared to your other directions, then your reshaped learning rate is going to move you in that, like it's going to prefer that direction to move in. Like think of it as like a reweighting of the gradient, right? And it's just preferring that direction. Where stamping the other ones, it could possibly even like increase the size in that direction depending on where you are in terms of that accumulation. Okay, this is important to do. We'll do this and we'll be done. So this is Adam. Besides stochastic gradient descent with momentum, this is like one of the most used optimizers. It looks very much like a combination of momentum and the Adagrad, right? You have these terms, these first moment terms, these second moment terms. So this looks like momentum, right? We're preserving, we have this exponential moving average of the gradient, and then our second moment is this exponential moving average of the square of the gradient, and then we do a gradient update with the momentum, with the first moment with the momentum term, and then do this adaptation with the outer term. The trouble with this is at the first time step, all of these terms are zeros, so there's like a little bit of a bias at the beginning. So the full atom is to do these two things like we just saw, but then there is this computing of an unbiased version of these moment terms that is not so. So when time is equal to 0, let's see, yeah, these just become ones. Yeah. Sorry, so these are never zeros. These are ones. So what you have is like a these values. We didn't point them out before, but these are values between 0 and 1. So these become smaller and smaller. So this, you're dividing by something that becomes closer and closer to 1. So this really changes the actual term that you use in the first couple of iterations, but as the number of iterations increases, this just becomes the first moment. It converges to the first moment and the second moment. So it's a way of kind of overcoming the fact that these are zero, these are near 0 at the beginning of the training, and this is sort of like beefs them up a little bit, just kind of increase them a little bit. But then you combine them in the way that we did before. Anyways, this is Atom, and it's probably like the first. It's probably like when you're starting a problem in optimizing, this is probably the first thing you're going to try. It usually works. You can usually do a little bit better with stochastic gradient descent with momentum, but you really have to tune it. And Atom will usually just kind of get you there really fast because it's just got a whole lot of bells and whistles built into it. So there were a couple more things here to go through, but they're not. There's like second order optimization that nobody ever uses because it's way too expensive with all the parameters that we have. Computing Jacobians and Hessians and things like that are just too expensive with the number of parameters. But some people have done this, including these awesome old dudes here. Okay, that's it. Thanks.